Welcome. In Chapter 4, we looked at how atoms can bond together with ionic and covalent bonds to form molecules. In this video, we will cover Chapter 5, Chemical Accounting, and look at how different atoms and molecules can react together to break and make new bonds in chemical reactions. A chemical reaction can be summed up with an equation. A chemical equation represents the sentences in the language of chemistry. When one molecule has the bond between its atoms break and a new bond form between other atoms, this is an example of a chemical reaction. In order for us to display these changes, we use chemical equations to communicate this chemical change using symbols and formulas that represent the elements and compounds involved in the reaction. First, let me draw your attention to the arrow. The arrow is the piece of the puzzle that signifies where we start and where we finish. Everything to the left of the arrow is going to be a reactant. This is the initial state of the molecules that are involved in the chemical reaction. Everything to the right of the arrow is the product. This is everything that is produced by the chemical reaction. This is the end result of the chemical reaction. So the reactants are the species present before the reaction. They're going to be on the left. And the products are the species that are present after the reaction. Those are going to be on the right. We're going to have some molecules turn into other molecules. The reactants turn into the products. The arrow means yield, or reacts to produce. When chemical reactions occur, they can be between molecules that are in a variety of different states. We can include this information in the chemical equation using subscripts. For example, a subscript with an S, that means that reactant is a solid. A subscript of an L, that means that that reactant or product is a liquid. A G represents a gas, and then finally an AQ represents that that molecule is part of an aqueous solution. When a chemical reaction occurs, we're taking chemical bonds that are existing within the molecule and breaking those bonds. Then the atoms within the molecule will form new chemical bonds with other atoms. Now, we also have to think about some of the laws that we've learned when we enact a chemical reaction. For example, the law of conservation of mass must be observed. The number of atoms and the types of atoms must remain the same before and after the chemical reaction occurs. The atoms just rearrange. You can think about it with a comparison to Lego blocks. If we were to take the Lego pieces apart of a Lego structure and then form a new structure, before and after, we can use the same number of Lego pieces in both examples. We're not creating or destroying any Lego pieces. We're not creating or destroying any matter. And then finally, the chemical reactions must be balanced. That means we need to have the same number and types of atoms in both the reactants and the products. In order to balance these chemical equations, we can use a coefficient. A coefficient is a number that we can place in front of a molecule, signifying how many of this type of molecule is used in the reaction. We can place coefficients in front of either the reactants or the products, and we can do this in order to balance out the number of each type of atom that's within the reaction. Now, we can't change the chemical formulas of the atoms within the reaction. The chemical formula represents that particular molecule. But what we can do is manipulate the number of each type of molecule that's engaging in the reaction. Let's look at an example. In this reaction, hydrogen gas, or H2, is reacting with oxygen gas to form water. Now, one thing you'll immediately notice is that in the reactants, we have 2 hydrogen atoms and 2 oxygen atoms. But in the product, we only have 1 oxygen atom. This means that we're going to need to use coefficients in order to balance this equation. Let's look at a couple examples of how not to do this. In the first example, we notice that there's one less oxygen in H2O than we had in our reactants. And so, one molecule of oxygen is added to the equation. This equation now has the correct number of atoms on either side. However, we broke a rule. We changed the formula and added a new molecule of O. This is not correct. Another example is to take H2 and O2 and turn them into H2O2. Now once again, we're changing the formula of the products. H2O is water. This is what we drink and what the seas and rivers are composed of. H2O2 is a different molecule called hydrogen peroxide. You might have seen hydrogen peroxide used to disinfect a wound. Now let's look at an example that uses coefficients. In this example, we take 2 molecules of H2 and 1 molecule of O2 to create 2 molecules of water. In our reactants, we have 4 total atoms of hydrogen, and we have 2 atoms of oxygen. And in the product, we have 4 atoms of hydrogen and 2 atoms of oxygen. In order to facilitate this, we used a 2 coefficient in front of the water and a 2 coefficient in front of the hydrogen with no coefficient in front of the oxygen. This is now an example of a correctly balanced chemical equation. Let's take a look at another example with a little bit more detail. In this reaction, we have a liquid, C3H5N3O9, that's reacting to form 4 new compounds. The nitrogen turns into nitrogen gas, the hydrogens turn into water, and then the carbons and oxygens turn into oxygen gas and carbon dioxide respectively. Now this example is a little bit more complicated. In order for us to make sure that the reaction is balanced, we can add up the total number of each atom on either side of the arrow. We can see the arrow here is in the middle, so on the left side of the arrow we have the reactant C3H5N3O9, and then we have our 4 products. As we go through and make sure that this reaction is balanced, we can count each of the atoms on either side of the reaction. In the reactants, we have carbons, 12 total, hydrogens, 20 total, nitrogens, 12 total, and oxygens, 36 total. You can get to these numbers by multiplying the coefficient by the subscript throughout the equation. Next, we want to count each of the atoms on the side of the products and make sure that they are balanced overall. We can see in the carbon dioxide we have 12 carbons, so carbons are balanced. Hydrogens are coming from our water molecule. 10 times 2 is 20, so hydrogens are balanced. Nitrogen comes from the nitrogen gas, which is a total of 12 nitrogens on the product side, matching the 12 nitrogens on the reactant side. And then finally we get to oxygen. Now oxygen is going to be a little bit more complicated. We have 10 oxygens from the H2O, we have 2 oxygens from the O2, and we have 24 oxygens from the CO2. So these add up total to get 36 oxygens, which match the 36 oxygens in the reactants. This equation we can say is balanced.